aspirants, so your midterm exams are ahead, and in today's video we are going to do the one shot of the chapter haloalkanes and haloarenes. Okay, so all the important concepts, definitions, name reactions, everything will be covered in this video, in just this one video. So please watch the complete video and make your notes so that you can master this chapter. So let's see what all things we have in today's class. So here are the topics. So first of all, we have here classification, nomenclature, nature of CX bond. These are very small topics. Then you have preparation of haloalkanes, preparation of haloarenes, physical properties, then here chemical reactions of haloalkanes and haloarenes, two separate topics are there, and then eighth one will be polyhalogen compounds. Okay, so this is very important topic here, which we will talk in detail. So let's start with classification. Okay, weightage here. So last year in 2025 paper, this chapter has 9 marks. And how was this 9 marks distributed? So in this there were 2 MCQs, or I can say 2 1-marker question, 1 5-marker question and 1 2-marker question. Okay, so there were 2 1-marker question, 1 2-marker question and 1 5-marker question. So 5, 6, 7, 8 and 9. Okay, so now let's move to the starting, that is topic 1, classification. And how do we do the classification? So there are basically 3 parameters of classifying these compounds. Okay, so the first one is the number of halogen atoms. Now before starting everything, let's just talk about what is haloalkanes, what do you mean by haloalkanes, and what do you mean by haloarenes, because this is our chapter name, right? So haloalkanes means you have an alkyl group R and then you connect it to X. What is X here? X is a I can say one is R, that is your alkyl group, and X is the halogen atom. Now this R group has to be a aliphatic group. Okay, now coming to haloarenes, you have AR here and X. What is AR here? AR is an aromatic ring, and when I talk about aromatic ring, we have just benzene here. So any benzene ring with a halogen group will be called as haloarenes, and any normal aliphatic chain, for example if I have CH3, CH2 and then X, so this is an aliphatic chain, right? So this is called as haloalkanes. Clear? Now let's understand the classification. So the first classification is based on the number of halogen atoms in a compound, or in a haloalkane or haloarene, how many halogen atoms are there. The second classification is the sp3-CX bond, means the CX bond, this carbon should be sp3 hybridized, and on the basis of that how many classifications we can have. And the next hybrid classification is sp2-CX bond. Okay, sp2-CX bond means this carbon should be having a double bond, so this is sp2 carbon. So on the basis of that how it is classified. Okay, so let's see this. First is on the basis of number of halogen atoms. It is very simple. If you have one halogen, then monohaloalkane, 2 halogen, dihaloalkane, 3 halogen, trihaloalkane. Similarly, if I talk about the aromatic compounds or haloarenes, you have 1 halogen, we'll call it as monohaloarene. If I have 2 halogens, you will call it as dihaloarene, and if I have 3 halogen atoms, we'll call it as trihaloarene. Okay, now let's move forward to the second category, that is sp3-CX bond. Okay, so remember in this the carbon which is attached to X is sp3 hybridized. sp3 hybridized means it has 4 sigma bonds. Okay, so what is sp3 hybridization? sp3 hybridization means it has 4 sigma bonds. Okay, now let's see the first one, that is alkyl halides, normal alkyl halides. Okay, so where you have this carbon, you can see whether it is sp3 hybridized or not. First check, this carbon is having 4 sigma bonds, it is sp3 hybridized. This carbon is also having 4 sigma bonds, this is sp3 hybridized. This carbon is also having 4 sigma bonds, so it is also sp3 hybridized. Now in this you can see there is a difference, primary, secondary and tertiary. So that, how can you decide this? The carbon which contains the X group, that carbon is attached to how many carbons? So for example, this carbon is containing the or bonded to halogen, it is attached to only 1 carbon, so this is a primary. Now this carbon which contains the X group is attached to 2 carbon, so it is a secondary. This carbon which contains the X group is attached to 3 carbon, so that is a tertiary. Okay, so the alkyl halides can be classified as primary, secondary and tertiary. That is the first classification. Next we'll talk about allylic halides. Allylic halides means what? So if I just break this compound and show you, so this is like this. Okay, now you see this carbon which contains the X group is attached to four other bonds, right? It is having 4 sigma bonds. So definitely it is a sp3 hybridized carbon. But now when it is sp3 hybridized carbon, if this sp3 hybridized carbon is attached to an sp2 carbon, okay, then we call this halide as an allylic halide. Okay, so if the carbon which contains the X group is attached to a double bonded carbon, then we call it as an allylic carbon or allylic halides. Okay, next we have benzylic halides. Benzylic halides is very similar to this allylic halides, but just you need to remember that we have a benzene ring here. So if a carbon which contains the X is attached to a benzene ring, then we will call it as benzylic halides. The carbon which contains the X group is attached to a double bonded carbon, that is a allylic halide. If the carbon which contains the X group attached to one carbon, then it is primary. Carbon which contains the X group attached to 2 carbon, it is secondary. Carbon which is attached to X is having 3 carbon, it is tertiary. Okay, so that is there. Next we will see here about the classification of sp2CX bond, means the carbon which contains the X is directly an sp2. Now what do you mean by sp2? It should have 3 sigma bonds. Okay, sp3 has 4 sigma bonds and sp2 has 3 sigma bonds. So now if you see this carbon, this one is there, okay, this is attached to X, and then we have one H here, right? So you can see 1, 2 and 3. There are 3 sigma bonds here. So this is an sp2 hybridized carbon. So when this sp2 hybridized carbon is directly bonded to X, it is called as a vinylic halides. Similarly, if you see here this carbon, okay, which contains these 3 bonds are there, right? These 3 are sigma bonds. Now when there are 3 bonds present here, okay, and then we will get a CX bond. This is again a vinylic halides. Next we have aryl halides when the X is directly attached to the benzene ring. Here also the X is directly attached to benzene ring. Okay, so that is your aryl halides. This is your vinylic halides. So very clear, vinylic halides means there is a carbon which is directly attached to sp2 carbon, that is called as vinylic, and if you have that sp2 carbon to which it is attached, it is a part of the benzene ring, or the X is directly attached to benzene ring, that is called as arylic halides, or this is what we call about haloarenes also. Now let's move to the next one. Coming to nomenclature. Okay, so nomenclature is very important. You just need to remember this common name also. Otherwise the basic rule is you have to first tell the position of the halogen and then the full structure of the compound. So for example, you can see here, if I have a structure like this, I have bromine here, so it is 2-bromobutane, right? So like this you can just tell which compound it contains, and based on that you have to name it. So next here it is another important structure is there about which I want to discuss in this, about vicinal and geminal dihalides. Vicinal and geminal. This is asked in the exam, so please remember. Vicinal means what? If you see the literal meaning, vicinal means vicinity or close to each other. So if 2 carbons or 2 adjacent carbons have X groups, then it is called as vicinal. And what do you mean by geminal? Geminal means when you have one single carbon having 2 X groups. Yeah, that is called as geminal. And how do we name them? So for vicinal, you can see here CH2Cl2. This is geminal. So for that we have ethylene. One second. Okay, so you will call it as alkylene. I'll write the common name here, or I'll just write the name of ethylene. Okay, ethylidene chloride. Okay, and when you have so for vicinal dihalides, the common name we used is alkylene dihalides. Okay, and for geminal, where you have 2 X group on the same carbon, we call it as alkylidene halides. Okay, Here we use dihalides, here we use alkylidine. Okay, this is very important. Next, we will see the nature of the CX bond. So first of all, if you see the CX bond, X is more electronegative, right? Carbon is electropositive. So this is a kind of polar bond, okay? Not very polar, but yes, it is a polar bond. Next, we will talk about the preparation of haloalkanes, okay? So there are different methods of preparation of haloalkanes. So we'll discuss all of them. So yes, so we can prepare haloalkanes from three main resources. The first one is using an alcohol, then from hydrocarbon, and then halogen exchange method. Now when I talk about alcohols, I'll show you how we can prepare that. Now when I talk about hydrocarbons, we have again two things. One is alkanes, one is alkenes. From alkanes, how can we prepare, and from alkenes, how we can prepare. When we prepare from alkenes, we have two methods, addition of HX and addition of X2. And then we have halogen exchange method, where we have Schwarz reaction and Finkelstein reaction, okay? So these are the three methods or three sources from which we can prepare the haloalkane. So let's talk about the first one. So I want all of you to draw this so that you can just see, it is like a mind map. When you have completed the chapters and when you want to revise, you need to open this and you see, okay, from alcohols, okay, this was the reaction. From alkenes, this was the reaction. So you could recollect. So that is why please prepare this and keep. I have made it for you. Please copy it down in your notebook. Now let's talk about alcohols. So using alcohols, how we can prepare haloalkanes. So the first one, your alcohol general formula is ROH. So you can use HCl and ZnCl2, you will get RCl plus H2O. You can use NaBr plus H2SO4, you will get RBr plus NaHSO4 plus H2O. You can use PX3 to get Rx plus H3PO3. You can use PCl5 to get RCl plus POCl3 plus HCl. Now these two reactions are very important. Fill in the blanks type questions are asked. You should also remember the byproducts here, okay? So I am marking here. Please remember the byproducts also. Next, we can prepare with bromine or iodine. If you use red phosphorus and X2, we can prepare Rx, and this is the most important method. Using SOCl2 also you can get RCl plus SO2 plus HCl, okay? Now remember that this method using SOCl2 is the most preferred method. Now what is the reason for that? It is most preferred because when you prepare this SO2 and HCl are gaseous byproducts, they evaporate easily. So in the container you are only left with RCl. So you can easily use that. Now here if you see there are certain byproducts, so you have to separate all the products to get your Rx, right? So that is why this is the best method. So this is about preparation from alcohols. So what all methods we have? HCl, ZnCl2, NaBr, H2SO4, you have PX3, you have PCl5, you have then red phosphorus with X2, and then lastly we have SOCl2. So 6 methods are there, please remember them. Now let's move to from hydrocarbons. So I told you hydrocarbons we have two things, one is from alkanes, another is from alkenes. So from alkanes we prepare using this method that is called as free radical halogenation. In that what you take an alkane, then chlorine in presence of HNu. HNu is the light source or the sunlight or energy, light energy that is required for this reaction. So what will happen? There will be free radicals generated and you will get multiple products. Your chlorine can be replaced here, chlorine H can be replaced, any of the H can be replaced with chlorine. Now remember, this is not a preferred method. Not a preferred method. Why? Because you get multiple products. You will not get one single product here which you directly want. You will get a mixture of products and then you have to do separation and all. So that is why it is not a preferred method. Next we will talk about from alkenes how we can prepare. So from alkenes again there are two methods. One is addition of HX, one is addition of X2. Now addition of HX follows Markovnikov's rule. Now those who have not remembered Markovnikov's rule, it was taught in class 11. And what is Markovnikov's rule? Markovnikov's tells you that X minus attaches to carbon with less number of hydrogen. Okay, now for example if you see I have taken propene, okay, and this double bond will break one double bond will break and both the carbon, one carbon H will be attached, to another carbon X will be attached. Now if you see that here only one hydrogen is there, here two hydrogen is there. So the carbon which is having less number of hydrogen, which one is that? This one, right? To that X will be attached. So this bond will break, X will attach here, H will attach here, H will attach here and X will attach here. Okay, so that is your formula of the product that we have got. Now there is also, we can add this this HX in the form of anti-Markovnikov's rule is also there. So I'll just discuss that. So if you have same propene and you are taking HBr in the presence of peroxide, H2O2, okay, in that case anti-Markovnikov's rule will be there. So only this one reagent is there which can show anti-Markovnikov's rule, so you don't have to confuse. Only if HBr with H2O2 is there, then only we will have anti-Markovnikov's rule. Or any peroxide, HBr should be there, and any peroxide, it can be benzoyl peroxide, it can be H2O2 also. Now when this is there, what will happen? The reverse will happen. The negative part, that is Br minus, will attach to the carbon having more number of hydrogen. So what will be the product here? CH3 CH2 CH2 Br, right? That will be the product. So we have got addition of HX. Now talking about addition of X2, so what will be, how X2 will be added? Once bond will break and two like single bond will break and then XX double bond will form. Next two XX bond will form. So this is which type of halides? If you remember, this is vicinal dihalides. Okay. Now moving forward to the halogen exchange method. So this is Finkelstein reaction and this is Schwarz reaction. In Finkelstein reaction, what happens? You take any RX, X can be chlorine, bromine, and you treat it with NaI dry acetone, you get Ri plus NaX. And then if you have Schwarz reaction, RX, AgF, any metal fluorides, you can take any of these metal fluorides, you will get Rf plus AgX. Okay, so with that we have completed the preparation of haloalkanes. Now let's see preparation of haloarenes. Okay, preparation of haloarenes, we have just two methods. One is from hydrocarbons, another is from amines. So how can we prepare from hydrocarbons? So you can take this is called as toluene. Okay, benzene with a methyl group is called as toluene. Yeah, toluene. So when you take toluene and you add X2 in presence of Fe and dark, means it should not have light in the, it should be happening in a dark condition. X2 in Fe dark medium, what will happen? You will get X present at ortho and para position. Ortho and para both will be forming. The reason here is CH3 is a ortho para directing group, okay, or it is a electron donating group. Okay. Next we have with this reaction with I2 is reversible in nature, so we don't get I2. It has to be like, then fluoro compounds are also not formed because they are highly reactive. So this X can be chlorine or bromine. Okay, clear? Then this one electrophilic substitution. Next we will talk about Sandmeyer reaction, okay, or from amines. So from amines to first we have to convert to benzene diazonium chloride. Okay, what we have to convert first? Benzene diazonium chloride. Okay, now what happens? How to convert that? Using NaNO2 and HX. Okay, once you get this, then you can convert Cu to X2. If you take X can be chlorine or bromine. If you can also use Ki, you will get iodobenzene. Okay, so you can get chlorobenzene, bromobenzene or iodobenzene, and this reaction is called as Sandmeyer reaction. So that is how we have done with the preparation of haloarenes as well. Now next topic is the physical properties. So what is physical properties here? Physical properties is melting points. First, melting point and boiling point, both of them we will discuss. So what is this? When you increase, when the mass increases, the boiling point increases. But at the same time, if the branching increases, then boiling point decreases. I'll give you an example. So for example, you have like this one compound, okay? You have like this one compound and you have like this one compound. So you can see as the mass is increasing, here 1 carbon, 2 carbon, 3 carbon. As the mass is increasing, suppose this is A, this is B and this is C. So the boiling point will be CBA. Okay, as the mass increases, the boiling point increases. Now suppose I have one compound like this. Okay, you have another compound like this. Okay, and yeah, so if two of these compounds are present, you can see here there is no branching, but here there is branching, right? So when branching is there, boiling point will decrease. So if this is A, this is B, then A will have more boiling point than B. Okay, that is what these 2 points tells you. Next, density. So as the mass increases, density will also increase, and solubility, they are less soluble in water because the bonds are not highly polar, or they are not able to form hydrogen bonds with water, but they are more soluble in organic solvent. And one more thing, solubility decreases as the mass increases, the solubility will decrease. Now let's talk about the chemical reactions of haloalkanes. Very important, very the most important topic here. Maximum of the questions will be asked from this one topic, that is nucleophilic reactions. So first of all, what are the chemical reactions shown by haloalkanes? So haloalkanes can show 3 types of reactions: nucleophilic reactions, elimination reactions, and reactions with metals. Okay, now what do you mean by nucleophilic reaction? So generally what happens, you have Rx, right? Rx is there. Now what is a nucleophile? Nucleophile is an electron rich species. Okay, it has very high electron rich species. Now what happens, if you see Rx, I have told you that X is highly electronegative, so it will have a delta minus charge, and this will have a delta plus charge. So what will happen, this nucleophile, since it is electron rich, this is electron deficient, will attack on this R group. Okay, and this X will go out. So what I will get, RNU plus X minus. So now what has happened, the nucleophile has substituted the X group, that is why it is called nucleophilic substitution reaction. I hope this is clear. Next we have elimination reaction, and then we have reaction with metals. In elimination reaction, always remember the product is one alkene group. Okay, product is alkene. Okay, so now we will see what are the nucleophilic reactions, and we have many things to study under nucleophilic reactions basically. So I'll move forward. Okay, so under nucleophilic reactions, first we will talk about different types of nucleophiles, then we'll talk about types of nucleophilic reactions, and then we'll talk about the stereochemical aspects. Okay, these 3 are very important. So first let's see the different types of nucleophiles. So I have just explained, I'll just draw once again. Rx will be there, one nucleophile will be there, nucleophile will attack on R, I'll get RNU plus X minus. Okay, now we will see what are the different nucleophiles that is possible, and what are the reagents that can be used for generating different types of nucleophiles. That is what we'll study under here. So if you see, one second, yes. So if you take NaOH or KOH, the nucleophile generated will be OH minus. So you will get ROH. Similarly, if you take water also, the nucleophile generated will be water, and the product will be ROH. Now if you take NaOR, the nucleophile is RO minus, and the product will be ROR. If you use NaI, the nucleophile is I minus, and the product will be Ri. Okay, so just imagine here what I'm saying. I'll just take first one. For example, you have Rx, and then I have taken this NaOH. Okay, so what will happen, this OH minus is my nucleophile, it will attack here, and I'll get ROH. Similarly, if I have Rx and I'm writing NaI here, so I minus is my nucleophile, it will attack here, and I'll get Ri plus NaX. Okay, next if you have ammonia, NH3 it is there, if you are taking ammonia, then I will get RNH2. If you have this is important, which are important here, these 4 are very important. If you use KCN, the reaction or the nucleophile will be Cn minus. If you use AgCN, the nucleophile will be NC. Okay, NC will be added, and the nucleophile will be AgCN, but the product that we get is NC here. And here if you use KNO2, you will get NO2 as the nucleophile. If you use AgNO2, AgONO is the nucleophile. So with KCN you will get cyanide, with AgCN you will get isocyanide, isonitrile or isocyanide you can tell. With KNO2 you will get alkyl nitrite. Okay, with KNO2 you will get alkyl ONO nitrite, and with AgNO2 you will get nitroalkane. Okay, I'll just repeat this one here clearly. So if I have Rx, okay, and if I take KCN, the product I will get is RCN. If you have Rx and if you take AgCN, then you will get RNC. That's the first thing you have to remember. Next, if I have Rx and if you take KNO2, you will get RONO. And if you have Rx and you treat it with AgNO2, okay, then you will get RNO2. Okay, so you can see the difference, and this is where people get confused, so you have to revise this one again and again. Okay, next, others are very simple, so we will move forward. You can just take this table. Now let's move to the types of nucleophilic reactions. Okay, so there are two types of nucleophilic reactions. One is called as SN2 mechanism, another is SN1 mechanism. So in SN2 mechanism, what happens? So what happens here, this is, so please see properly. Okay, I'll use this color. Okay, so now what you see, this is Rx. Okay, this is nucleophile. Okay, now what happens, the nucleophile attacks the Rx from the backward side. It attacks from the backward direction, and there is a position where the nucleophile is also attached, and this is called as your leaving group, which is leaving. This X is your leaving group. Nucleophile is attacking. So this position where you have the nucleophile, you have the X, and this is called as a transition state. Okay, and then you find this nucleophile has attached and the leaving group has left. Okay, example, if you see, you have this CH3Cl, OH minus is attaching. OH minus will attack from the back side, so there's a transition state formed here. So at the transition state, you can see carbon is having 5 bonds. This is also important point, 5 bonds are there. Then what will happen, this bond will form, this bond will break, so you will get a compound like this. This is called as SN2 mechanism. Now let's see some important points for SN2 mechanism. Okay, so first of all, it is a bimolecular reaction. Okay, reaction type, its name is SN2 reaction. What is the kinetics of this reaction? So if you see from the starting of the reaction, when the reaction is started, you have both Rx and Nu in the medium. So the reaction rate will depend on both Rx and Nu. So it is a second order reaction. Okay, so if I have this one, to follow second order kinetics, because rate depends on both nucleophile and the alkyl halide concentration. So if I want to write the rate law for this one, so rate will be equal to K into concentration of Rx into concentration of nucleophile. Okay, that is how I can write it. Next, how many steps are involved? It involves only one step. Okay, the reaction happens in one step. The nucleophile attacks from the backside and the X group slips. It is a single state. Then transition state, yes, there is a transition state is formed where the carbon has 5 bonds at one time. Next, the carbon structure, when you see in the transition state, when this is formed, right, you can see the transition state, all these 3 carbons are in one plane. Okay, and you have this carbon and this 3 bonds are in one plane. So that is what is written here. All the 3 CH bonds lie in the same plane during the transition state. Next, about inversion of configuration, yes, the carbon shape flips like an umbrella in a strong wind. This is called as Walder inversion. So if you see now, earlier the leaving group was attached on this side. Okay, and now the nucleophile is attacking on this side. So the reverse happens, so the inversion of configuration happens. Next is effect of bulky groups. So bulky substituents near the carbon make it make it hard for the nucleophile to attack, so reaction slows down, and the order is primary, secondary and tertiary. This is very important. Here also majority of the questions will be asked from here. Primary group, so you see here what is the mechanism happening. This nucleophile has to attack from the back side, right? So these groups should be having less hindrance. If they are putting more hindrance, then the attack of this nucleophile will be very difficult. So that is why the order is 1 degree, 2 degree, 3 degree. In 1 degree, these are all H molecules, so small, less hindrance. In 2 degree, what will happen? There will be 1 carbon and 2 hydrogen. In 3 degree, there will be 3 carbon and 1 hydrogen. So that is why there will be a difference, right? So there will be more hindrance. Now let's talk about next mechanism, which is your SN1 mechanism. So in SN1 mechanism, actually there are 2 steps involved. So let's see the first step. Here what happens, in step 1, this Rx, right, this X is called as leaving group, right? So this leaving group leaves, and what we get a carbocation here in the step 1. And then what happens in step 2, this nucleophile, okay, now nucleophile can attack on this carbocation to get the product. Okay, now this nucleophile, when we have this carbocation, this is called as a intermediate. Okay, it is an intermediate, and this is a planar structure. Okay, this is a planar structure. So what will happen, this OH minus is also a planar. Now this OH minus can attack on this carbocation. It can attack from both sides. It can either attack from the front side or it can attack from the back side. Okay, so we'll study about this in detail. So let's see some points about SN1 mechanism first. What is this kinetics? So if you see, the rate of a reaction is determined by the slower step, right? So this is the slow step and this is the fast step. Now in the slow step, there is no nucleophile presence, only the Rx is present. So the rate of the reaction depends only on Rx and not on the nucleophile, right? So what will happen here? You can see that in the rate of the reaction, so it follows first order kinetics, and the rate only depends on the concentration of the alkyl halide. Next steps, it has 2 steps. One is the breaking of CBr bond and the second one is the attack of the nucleophile. Solvent preference, so here in case of SN1 reaction, we generally prefer polar protic solvents like water and alcohol. Stability of carbocation, yes, 3 degree, 2 degree, 1 degree. Okay, so the SN2 mechanism reaction rate was 1 degree, 2 degree, 3 degree. In SN1, it is 3 degree, 2 degree, 1 degree. Okay, I'll just write it here for more, one second. I'll just write down here for more clarification. SN2 reaction order is 1 degree, 2 degree and 3 degree. In SN1 reaction, the order is 3 degree, 2 degree and 1 degree. There the reason was steric hindrance is less than 1 degree, and here since the carbocation is formed, the stability of carbocation will determine the order of the reaction, and 3 degree is more stable than 2 degree, 2 degree is more stable than 1 degree. So this is the order for SN1 reaction. Now moving forward here, the allylic and benzylic halides also shows higher rate of SN1 reaction because their carbocations are highly stable because of the resonance. Allylic, if you see, this is allylic, right? Now this X moves, here we will get a positive charge. Now there is resonance here, so this carbocation is highly stable. So even though it is primary, it will show SN1 reaction. Similarly, cases for benzylic also. Benzylic is like this. Okay, now if this X goes, here there is double bonds are there. Once this goes, we'll get a carbocation and this will form a double bond. Okay, it will stabilize with resonance. Then what is the reactivity of halides? So here what is the first step? The first step is the breaking of this CX bond, right? So if this CX bond is weak, then the reaction will be faster. So that is why the order is Ri, Rbr, Rcl and Rf. I minus is the best leaving group because the bond is very weak between Ri. Okay, so what we have understood here, if this R is same, okay, Ri, we have Ri, Rbr, Rcl and Rf. This R is same in all the cases, and this is the different thing, then this one will react faster. Now if you have this X is same, okay, you have CH3X, you have CH3X and you have CH3 whole X. Now you see this is 3 degree, this is 2 degree and this is 1 degree. When the X is same or when the leaving groups are same, this 3 degree will be more reactive than 2 degree, 2 degree will be more reactive than 1 degree. Okay, now let's move forward to nucleophilic reactions, stereochemical aspects. Okay, so there are certain things that we should know about stereochemical aspects. So the first thing is optical activity. Now what do you mean by optical activity? So any compound which can rotate, plane polarized light. Okay, plane polarized light. If a compound can rotate plane polarized light, then that compound is called as optically active. Okay, or now how will you know whether a compound is optically active or not? So you have to take that compound to the lab and you have to pass plane polarized light through that sample. When the light passes the sample, if the light is like bent or if the light is rotated, then we can say that okay, this molecule is optically active. But is it practically possible to go every time to the lab and check whether it is optically active or not? No, right? So to help you with this, what happens, there is something called as chirality, okay, or asymmetric. Okay, so now remember, if a carbon forms 4th bond, if a carbon has 4 different groups attached to that, then we call it as a chiral carbon, or the carbon is an asymmetric carbon. So if the molecule is chiral molecule, then it will be optically active. Okay, that's the first condition for a molecule to be optically active. How can you see the molecule and say whether it is optically active or not? So if a carbon has 4 different bonds, then that molecule is chiral or asymmetric in nature, and that molecule will be optically active. If it is optically active, it will rotate the plane polarized light. Okay, now what is there in enantiomers? What do you mean by enantiomers? So now see, suppose this molecule, okay, this molecule is there which is rotating the plane polarized light. Now this molecule will have its mirror image also. It can have one of its mirror image like this. Okay, now these 2 pairs will be called as enantiomers. So how will you define enantiomers? Enantiomers are non-superimposable mirror images of each other. Okay, let me tell you now like this. You found one compound, okay, it is chiral. Chiral means what? It is optically active. Optically active means what? It will rotate the plane polarized light. Now this compound's mirror image, okay, will be this molecule and its mirror image will together form a pair called as enantiomers. How do we define enantiomers? Enantiomers are the non-superimposable mirror images of each other. What do you mean by the word non-superimposable? So see, suppose I have this letter A, okay, I draw its mirror image. Okay, now I can take this exactly A, and if I keep on it, this will overlap with this one. But if I have letter B and I take its mirror image, it will be like this. Now if I take this B and keep on this one, it will not overlap, right? So similarly, the chiral molecule and its mirror image, these are non-superimposable images of each other, or non-superimposable molecules, and this together, this pair is called as enantiomers. Now how do they work? So for example, you have a compound like this. I'll draw like this. Okay, this is one molecule. Okay, so you can see all the 4 groups are different attached to the carbon. So I can say that this molecule is chiral. Now if the molecule is chiral, I can say that it is optically active. Right, now if I am saying that it is optically active, what it will do? It will rotate the plane polarized light. Right, now suppose rotation can happen in 2 directions. It can either have clockwise or anti-clockwise. So if you see, you have a sample, okay, you are passing the plane polarized light through this one. It is having plane polarized light means having only one field. Now when it has rotated, it can either rotate in this way or it can also rotate in this way. Right, so suppose this compound is rotating in clockwise direction. I am denoting plus for clockwise direction. Then its mirror image will be there. Okay, how can I draw the mirror image like this? This is the mirror image. Okay, so now this compound will have, this compound is also optically active because it is also having 4 different groups. it will rotate the plane polarized light in anti-clockwise direction. This is in clockwise direction, this one will be in anti-clockwise direction. So now these two compounds together are called as what? Enantiomers. Okay. So enantiomers are optically active isomers which are non-superimposable of images of each other, and if one rotates the light in clockwise, the other will rotate in anti-clockwise direction. Clear? Fine. So this is all about enantiomers. Now what is this inversion, retention and racemization, and where do we have to use it? So this is with respect to our SN1 and SN2 reaction. Now if you see SN1, SN2 reaction, okay, so what happens there? You have group like this, okay, nucleophile comes, it attacks from the opposite side. So now what will happen? You will have nucleophile like this. You have groups, sorry, like this. So now you see this has actually inverted, means the nucleophile has attacked from the opposite direction. So whatever was the reactant, the product will be one inverted configuration of that. Okay. And if I talk about next, if I talk about SN1 mechanism, SN1 mechanism. So you have suppose 4 bonds. In the first step what happens? This X goes out. So now this is a planar molecule. Now in step 2 what happens? In step 2 the nucleophile will attack, right? So when the nucleophile will attack here, you have possibilities like this. Okay, nucleophile can attack from this side and the nucleophile can also attack from this side. Okay. Now see, the X was on this side. So this product is having the same configuration as the reactant molecules. This is called as retention molecule. And this one is having the opposite configuration of the reactant molecule. So this is inverted product, inverted and retention. Now the mixture of this retention and inverted product, okay, you have 50% retention, 50% inverted. This mixture of these two products is called as a racemic mixture. Okay, so in SN2 mechanism we will get inverted product, but in SN1 mechanism we will get a racemic mixture. Okay, so now these two are mirror images of each other, non-superimposable mirror images of each other. They are 50-50%. So if this molecule, so in the sample, so for example you have this container, okay, you have taken this compound, this compound you have taken, you added nucleophile. Okay, after the reaction has happened, what I will get here? After the reaction has happened, you will get a compound like this. Both the products will form in equal equal amount. So I have a nucleophile on this side where the X was present, and I also have the nucleophile on this side, on the opposite side. Like this 50-50% product will form. Now when you pass the plane polarized light, this one will try to rotate the plane polarized light in clockwise direction, this one will try to rotate in anti-clockwise direction. So equal and opposite force will apply, so the light will pass as it is, because if it is rotating clockwise, it is again bringing it to anti-clockwise, right? So that is why the racemic mixture will have this mixture will now be called as optically inactive, because it is not able to rotate the plane polarized light. See, individually both of them are optically active, but when you mix them, that too in equal proportion, and when you have a racemic mixture, the mixture will be called as optically inactive. Okay, so this is all about the stereochemical aspects of this one. So I hope this is clear. Now we'll talk about elimination reaction. So in elimination reaction, what happens? You take a base or something like this. Okay, a base is taken and then it reacts with, it abstracts one of the acidic proton, and when it abstracts one acidic proton, you get a alkene formed here. Okay, an alkene is formed, and this type of reaction is called as your elimination reaction. And there is a rule that we follow in elimination reaction, that is Saidzev rule. Okay, so you can see here, suppose I have bromine at this position, I have OH on both the sides to X so if this is the carbon containing the X group is alpha carbon, the next carbon which contains the hydrogen is beta hydrogen. So if I have this alpha carbon here, this is beta hydrogen and this is also beta hydrogen. So what will happen? The leaving group or the OH minus can attach abstract the H here, or the OH group can abstract the H here. Now if it abstracts here, there will be a double bond here, and there will be, if this is abstracted, there will be a double bond here. Now which is a major product? This is spent 1 ENE, this is spent 2 ENE. So which is a major product here? Now if you see, if there is double bond, okay, and there will be 4 bonds, right? If more carbons are present, okay, more number of carbons are present, then it is more stable product. Okay, so let's see this product. You have CH3, CH2, CH, double bond. Okay, so if you see, there are 2 carbons beside this double bond. Now if I see here, CH3, CH2, CH2, then I have this one CH, double bond, CH2. Now if you see here, there is only 1 carbon is there, all other 3 are hydrogen. So which will be more stable? This one will be more stable. And who told us this one? It is given by Sedzeff rule. Now let's move forward to the reaction with metals. So here we have, one is organometallic reactions, another is Woods reaction. So organic metallic reaction, just take on haloalkane and take Mg, then you will get MgBr, and this is called as Grignard reagent, very important reagent in organic chemistry. Now we have Woods reaction. If you take Rx and Na, okay, then what will happen? You will get RR plus NaX. So this reaction is used to double the number of carbons. If you have 1 carbon here, you will get 2 carbon, 2 carbon you will get 4 carbon, 3 carbon you will get 6 carbon. Okay, so that is all about the chemical reactions of haloalkanes. Now let's talk about the chemical reactions of haloarenes. So here also I have 3 types of reactions: nucleophilic, electrophilic, and reaction with metals. Now in nucleophilic reactions, you have to understand that haloarenes are very much less reactive to nucleophiles. Okay, they do not show nucleophilic reactions easily. Now what is the reason for that? First is your resonance effect. Now see, in a nucleophile reaction, what should happen? This is X, this is nucleophile, right? Nucleophile should come here and X should go, right? That should be the normal reaction happen. But here what happens? This lone pair of X is in resonance. So there is a partial double bond character here. This bond is very strong. So it is not easy that a normal nucleophile will come and remove the X. So that is the resonance effect. After that, the second point is this carbon to which the X is bonded is an sp2 hybridized carbon. Now sp2 hybridized and X bond is very strong as compared to an sp3 and X bond as we see in haloalkanes. So that is the second reason why this reaction is very difficult. Next, the instability of phenyl cation. Once this X, suppose somehow this X leaves also, so what will be formed here? X will form, plus charge will get, this is an sp2 carbon which is highly electronegative. So a positive charge on an electronegative atom is again very unstable. So because of these reasons, we cannot find nucleophilic reactions that easily in case of haloarenes. But does that mean that there is no nucleophilic reactions? No, it has nucleophilic reactions, but at certain conditions. So if you see, initially if you just take Cl and OH minus, you need 623 Kelvin and 300 atm of pressure. But what if you add one NO2 group? So what exactly this NO2 group is doing? It is reducing the electron density. It is an electron withdrawing group. It reduces the electron density so that the nucleophile can attack easily, right? So because nucleophile is electron rich, if this becomes electron deficient, the nucleophile can attack. So that is why what happens, we get here at, if you take one NO2 group at 443 Kelvin also the reaction can happen. If you take 2 NO2 group at 368 Kelvin the reaction can happen. If you take 3 NO2 group with warm temperature also the reaction can happen. Okay, so that is how we can do nucleophilic reactions in case of haloarenes. Now coming to electrophilic substitution, so there are, so it is normal to what we have studied in benzene in like if you remember in class 11, benzene reactions are given. It is similar to that. So first of all, for halogenations you need chlorine and FeCl3. The substitution will be at ortho and para. Okay, then for nitration you have concentrated HNO3 and H2SO4, so nitro group can be added at ortho and para position. Then for sulfonation, concentrated H2SO4 again at ortho and para position. Next you can take Friedel-Crafts acylation and Friedel-Crafts alkylation. So alkylation you use CH3Cl AlCl3, so CH3 group will be added at ortho and para position. Similarly for Friedel-Crafts acylation, CH3COCl AlCl3, you have at ortho and para position. Okay, these are the electrophilic substitution reactions of which one? Of haloarenes. Then coming to reactions with metal, so we have Fittig reaction and Wurtz-Fittig reaction. So if you remember, Wurtz reaction we had Rx. In Fittig reaction you have ARX with Na and dry ether. Now this is Fittig reaction. Now when you mix Wurtz and Fittig, in Wurtz we have used Rx, in Fittig we have used ARX, and if you react both of them in presence of Na, you will get this one. Okay, this is Fittig and Wurtz-Fittig reaction. Now we will talk about polyhalogen compounds. So there is not much here. This is something very theoretical. Just there are some polyhalogen compounds that we use in our daily life, and there are some compounds which are highly poisonous and toxic. So we have to more focus on this one, Freons and tetrachloromethane. Okay, these are two important compounds, others you can just overlook. So let's see first of all dichloromethane. So what is the structure of dichloromethane? You have like this. This is dichloromethane, geminal dihalide, right? So what are its uses? You can see it is used as a solvent. And what are its harmful effects? Dizziness, impaired hearing and vision. Then you have indirect skin contact also can cause a problem. It can even burn your cornea if you have direct contact with eyes. Now let's see next trichloroethane. So this is important. Trichloroethane, you have CHCl3. We also call it as chloroform. Okay, so uses, again it is used as a solvent. This reaction is important. So what we do is this chloroform is always stored in dark bottles. The reason is when it is present in form of, if light is present, it reacts with oxygen to give you COCl2 plus HCl. Now this harmful gas COCl2 is very, very toxic, and it is called as phosgene and can create harmful effects. Now next one we have triiodomethane. So this is, iodine is used as an antiseptic, that you should be knowing. Next we have tetrachloromethane, that is CCl4. It is used in the refrigerants, that is important, and low high level what can happen, that is there, and it is also responsible for the depletion of ozone layer, that is important. Now next one which is very important is Freons. So Freons are what? The chlorofluorocarbon compounds of methane. Okay, chlorofluorocarbons compounds of methane, and there is one particular Freon, that is Freon 12, which we call it as CH2Cl2F2. Okay, and this is prepared using Schwartz reaction, that you should remember. What is it used, and harmful effects we know. Freons are used for ozone not used, they are the causes of ozone depletion, and because of that there are so many consequences like climate change, global warming, and etc. Next we have DDT. So it is a compound which was used as insecticide a long time ago, but due to its non-biodegradability it was banned. Okay, but the structure of DDT you should remember, this is the structure of DDT. Okay, so with this I have completed the one shot of this chapter. Now let me tell you, if you want to study this chapter much more in detail, in much more interesting way, you can watch our Sankalp series. Okay, and there I have taught this chapter in 4 to 5 parts. Small videos are there, but with so much I can say like storytelling is there, so you can understand it in a better way. If you are not if you think this is too fast, so you can go there, and the stereochemical aspects I have explained in such a beautiful way, so you can try and watch that. Okay, so that's all in this video, and for midterm this is fine, you can just revise this, and then in the next video I'll bring out the most important questions. So just revise this, watch that video, and this chapter is done for you. So thank you for watching once again, all the best, and please start studying for your midterms. Any doubt you have, put down in the comment section, I'll definitely address it.